Imagine a computer that thinks like you, it learns like you, it even makes decisions like you. This isn't science fiction, this is the exciting world of neuromorphic computing. Neuromorphic computing represents a fundamental shift in computer science. It moves away from traditional methods and embraces a new paradigm inspired by the human brain. Instead of relying on separate processing and memory units, neuromorphic computing integrates them. This mimics the brain's interconnected structure. This approach allows for parallel processing and real-time learning. These capabilities are at the heart of human cognition. Neuromorphic computing aims to replicate these capabilities in silicon. This opens up exciting possibilities for the future of artificial intelligence. Traditional computers are like well-organized filing cabinets. They are designed to store vast amounts of information in a structured and easily retrievable manner. They excel at storing information and performing calculations quickly, processing data at incredible speeds that are unmatched by any other technology. However, they struggle with tasks that require flexibility and learning, such as recognizing images or understanding natural language. These tasks demand a level of adaptability that traditional computers lack. Neuromorphic computers, on the other hand, are like the messy, interconnected networks of neurons in our brains. They mimic the brain's architecture, allowing for more dynamic and flexible processing. While they are not as fast at crunching numbers as traditional computers, their strength lies in their ability to learn and adapt. Neuromorphic computers excel at adapting to new information and solving complex problems that often stump traditional computers. They can handle tasks that require a high degree of learning and pattern recognition. Imagine teaching a computer to recognize a cat. This task highlights the differences between traditional and neuromorphic systems. A traditional computer needs to be fed thousands of images labeled cat to learn what a cat looks like. It relies on sheer volume to make accurate predictions. Even then, it might struggle with variations in breed, lighting, or pose, often failing to recognize a cat if the image is slightly different from what it has seen before. A neuromorphic computer, like our brain, can learn from fewer examples and generalize better to new situations. It can recognize a cat even if it has only seen a few images, adapting to new variations with ease. This difference in approach makes neuromorphic computing particularly well suited for tasks like image recognition, natural language processing, and robotics. These are areas where the ability to learn and adapt is crucial. Traditional computing often falls short in these areas, struggling to keep up with the demands of modern AI tasks. The future of computing may well lie in the development and refinement of neuromorphic systems, which promise to bring us closer to the adaptable, intelligent machines we envision. The human brain is an extraordinary organ, a marvel of biological engineering that has evolved over millions of years. It can process vast amounts of information, learn from its experiences, and make complex decisions with remarkable speed and accuracy. All of this is achieved with an energy efficiency that puts even the most powerful supercomputers to shame, operating on just a fraction of the power. The secret lies in the brain's unique architecture and communication method, which is fundamentally different from traditional computing systems. Neurons, the brain's fundamental building blocks, communicate with each other through electrical impulses called spikes, which are brief, rapid bursts of electrical activity. These spikes are not continuous but occur in discrete bursts, allowing for efficient and precise communication. This is similar to how we perceive time as a series of moments rather than a continuous flow, breaking down complex processes into manageable chunks. Neuromorphic computing borrows this concept of spike-based communication, mimicking the brain's method to create more efficient and powerful computing systems. Instead of using continuous values like traditional computers, neuromorphic systems use pulses or spikes to represent information, which can lead to significant improvements in processing speed and energy efficiency. This approach, known as spiking neural networks, or SNNs, allows for much greater energy efficiency, making them ideal for applications where power consumption is a critical concern. The potential applications of this technology are vast, ranging from more efficient artificial intelligence systems to advanced robotics and beyond. As we continue to explore and develop these brain-inspired systems, we may unlock new levels of computational power and efficiency, paving the way for the next generation of technological innovations. The power of spikes is not just a fascinating aspect of neuroscience, but a gateway to the future of computing, where the boundaries between biology and technology continue to blur. Mimicking the brain neuromorphic chips in action. Neuromorphic chips are designed to mimic the brain's structure and function. Unlike traditional chips that separate processing and memory, neuromorphic chips integrate these functions. This allows for faster and more efficient computation, particularly for tasks involving learning and adaptation. Imagine a neuromorphic chip designed for image recognition. As the chip receives visual information, artificial neurons on the chip fire spikes in response to specific features. These spikes trigger other neurons, forming a network of activity that represents the image. With each new image, the connections between neurons strengthen or weaken based on the success of the recognition. This process, known as synaptic plasticity, is how the chip learns and improves its accuracy over time. Efficiency is key to the neuromorphic advantage. The human brain operates on roughly 20 watts of power, about the same as an energy-saving light bulb, yet it can perform tasks that would require a supercomputer consuming megawatts of power. This remarkable efficiency stems from the brain's unique architecture and spiking-based communication. Neuromorphic computing aims to replicate this efficiency. By using spiking neural networks and integrating processing and memory, neuromorphic systems consume significantly less power than traditional computers, especially for tasks involving learning and real-time processing. This efficiency has significant implications for the future of computing. As we generate ever-increasing amounts of data, traditional computing approaches face limitations in power consumption and heat dissipation. Neuromorphic computing offers a more sustainable path forward, enabling us to process vast amounts of information with minimal energy expenditure. The future is neuromorphic. From robots to medicine, the potential applications of neuromorphic computing are vast and varied. Imagine robots that can learn and adapt to their environment in real time, just like humans do. Picture medical devices capable of analyzing complex biological data to diagnose diseases with unprecedented accuracy. In robotics, neuromorphic computing could lead to the development of machines that can navigate complex environments, interact with humans more naturally, and learn from their experiences to improve their performance. These robots could revolutionize industries like manufacturing, healthcare, and exploration. In medicine, neuromorphic devices could analyze medical images, genetic data, and real-time patient monitoring information to provide earlier and more accurate diagnoses. This technology could also pave the way for personalized medicine, where treatments are tailored to an individual's unique biological makeup. Neuromorphic computing, a glimpse into the future. Imagine a world where computers can think and learn like humans, where machines can adapt to new situations and solve problems with the same efficiency and creativity as the human brain. Neuromorphic computing represents a paradigm shift in computer science. This groundbreaking technology mimics the neural structure and functioning of the human brain, offering a new approach to processing information. Inspired by the human brain, this technology has the potential to revolutionize artificial intelligence, leading to machines that can learn, adapt, and interact with the world in ways we once thought impossible. Imagine robots that can understand and respond to human emotions, or AI systems that can diagnose diseases with unprecedented accuracy. While still in its early stages of development, neuromorphic computing is rapidly advancing. Researchers around the globe are making significant strides in creating more efficient and powerful neuromorphic chips. As research progresses and technology matures, we can expect to see neuromorphic systems playing an increasingly important role in our lives. These systems could lead to more intuitive and responsive technologies, enhancing everything from our daily gadgets to complex industrial systems. From self-driving cars to personalized medicine, the possibilities are truly limitless. Imagine vehicles that can navigate through traffic with the same skill as a human driver, or medical treatments tailored specifically to an individual's genetic makeup. As we stand on the cusp of this exciting new era, one thing is clear. Neuromorphic computing is poised to reshape our world in profound ways. This technology could lead to breakthroughs in fields we haven't even imagined yet, opening up new frontiers in science and technology. By harnessing the power of the human brain, we are unlocking a future where machines can augment our abilities and help us solve some of humanity's greatest challenges. From tackling climate change to exploring the depths of space, neuromorphic computing holds the key to a future where technology and human ingenuity work hand in hand to create a better world for all.